So the second part of the thermodynamic topic would be about enthalpy of solution. Okay. I mentioned before how important is to be confident with the Hess's law and overall the concept, because it can be applied to more complex calculations, like Born-Haber cycle that had a lot of steps that that we need to use the value for, and we can use it for this concept as well, the enthalpy of solution. So there are slightly new definitions. So the important thing is to go through them first. And remember, definition and equations is the thing that we need to recognize of the enthalpies. So enthalpy change of solution. I'm going to write the equation and we can explain that. But it's always the enthalpy change when 1 mole of something. And in this case, it's 1 mole of ionic substance dissolves in water to form a solution. So we have an ionic substance. Let's take a simple one, sodium chloride. Ionic substance dissolves to form the aqueous solution. Okay, so simply change in state, the energy involved in this one. Okay, that's solution. One more enthalpy that we need to introduce, which is the enthalpy change of hydration. Hydration, you may have heard of that before, is the process when the ions in an ionic lattice, they are separated and surrounded by water molecules, because water is polar, surrounds these ions that were before in the ionic lattice. So the ions involved here are sodium, and we know that these ions in their state is gas, so you know that this comes from the ionization of the ionization energy, okay, gaseous ion. It becomes sodium aqueous, okay, and then there would be a second one, of course, because we have two different ions, gaseous chloride ion to gaseous to aqueous chloride. Okay, so this you can write it like this, or sometimes you also add the aqueous sign. So for example, if there is a change in state like this, because in theory is a mixing with, like, it's not reacting chemically with water, okay, but it's still forming an interaction with water. That's why you can write it like this, plus AQ. So in all of these reactions, it's just because you are reacting it with water. Okay, those are the two new definitions. Solution enthalpy change when 1 mole of ionic lattice dissolved in water to form they call it infinite dilute solution because it's just completely diluted. Hydration enthalpy change when 1 mole of a gaseous ion dissolves to form again an diluted solution. The third enthalpy involved here is one that you know already, which is the lattice enthalpy. So the lattice enthalpy is the enthalpy change when 1 mole of ionic lattice is formed from its gaseous ions. We can actually distinguish two different enthalpy, because this one is the lattice enthalpy when the ionic lattice is formed. The opposite one, so when the ionic lattice is broken down to its gaseous ions, it's called lattice enthalpy of dissociation, separating the ions. It's all logical, so think about the definitions, what they make sense. Now, before we move on, I want you to take a moment to think about how are these enthalpy related? Could you put them in a cycle like Hess's law? I want you to remember this theory, A, B, C cycle, where C is something that this A and B, which is the reaction that we need to find the enthalpy of, have in common. Okay, take a moment to try to put these three equations in this like cycle form to see how they are related so that we can work out the equation. One thing to consider is what is common between these equations. So the common either product or reactant is just this. the sodium chloride solid. Notice that it appears in both of these equations. And this sodium chloride aqueous, you can also write it as the ions, okay? Because it's an ionic compound in aqueous solution, it is going to be separate as ions. So writing it like this and like this, it's the same, right? Because they're going to exist. So let's say that instead we write it like this. Maybe this makes it easier to see how these are related, okay? But maybe like this, you've identified what's that common thing that you can add. And then you can kind of arrange it as you want, but give it one more try and then otherwise I will write it down. It's challenging to put these equations together in a cycle, but there is a method, there is a way, and this can help you if you have unfamiliar reactions and in general for the concept of Hess's law. So take one equation, any of this. I would start with this first one, sodium chloride as solid, that goes to sodium ion, so the enthalpy of solution, and chloride ion. Okay. This, is it connected or is it the reactant or the product of another equation? Yeah, it's this one. So if you look at this equation, sodium chloride is formed by sodium ion and chloride ion. So we would write it like this. Sodium as gas plus chloride as gas. Okay? Because it's, as you can see, connected. Yeah, it's the product. And here is the reactant. So we can look at each part of that equation that you want to have in the middle. And then you think, okay, is this reactant something connected to another equation? So think about this one. Is it reactant or product of something connected to this? Because the one that we wrote for last. Actually, yeah. These aqueous ions are the product of the enthalpy of hydration. This means that this arrow will go up. So notice how by taking one equation, doesn't matter which one, then you look at reactant and product and you think about, okay, is that related to the other enthalpies that we have? And in this case, it is. So enthalpy change of solution up here, gaseous ions to solid, we know that is the lattice enthalpy, and gaseous to aqueous, we know that is the hydration enthalpies. And then this goes back to the simple Hess's law. Can you try to work out the equation? Let's say that we don't have the enthalpy of solution and that's what we want to find. Do you remember how to use the cycle to find that? Give it a go. As simple as that, what Hess's law states is that to find the enthalpy of a reaction that we can't find directly, we go the other way around, and then we look at the direction of the arrows. We see that the lattice enthalpy is the opposite direction, yeah, while the hydration enthalpy is the same direction. So we know that it would be enthalpy change of hydration minus the enthalpy change of the lattice enthalpy. Okay, so that was the same way that we used to find the equation for formation and combustion cycle. Okay, remember that the minus simply means change in sign of that enthalpy. Okay, good. And I hope it makes sense. So of course we need to consider as usual the ratio. In this case is all 1-to-1, so it's simple, but if you have more ions involved, of course you would have to times the hydration enthalpy by 2, for example. So these are little things that we need to keep in mind. Now let's try to apply this, and there are many ways you can work this out. You know an equation, or maybe like you either remember the equation if it's hydration is equal to lattice plus solution. Okay, that's one way, or you work out the cycle, okay, by simply doing the equation. Just for the sake of your practice, I would suggest you do the equation because you're also asked to write definitions and the equation to define these enthalpies. So it's useful to practice like this. But anyway, for this exercise, you should try to find the enthalpy change of hydration of calcium ion. Okay, take your time, maybe around 5 minutes to give it a go. So as shown here, one alternative to do the exercise is to the cycle. And with the cycle, it's kind of the logical way to work it out because you know either the definition or you're given the equation, something you can work out. Yeah. In fact, here it's correct in writing. So according to this cycle, this is the enthalpy change of so the aqueous ion to this. It's actually the other way around. This one. So let me just redraw it for clarity. Okay, so we have and then I'll take back the values. So let's start with the enthalpy. So we have enthalpy change, remember, of solution, of hydration, and lattice enthalpy. Okay, and we can start with the solution enthalpy change when 1 mole of ionic compound, here we have this calcium bromide, forms its, or is dissolved to form an aqueous solution. And we know that the ions do split up. Okay, so we have 2 bromide. We need to consider that Br minus aqueous. Enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ion forms the aqueous ions or is dissolved to form a diluted solution. So the gaseous ions, keep in mind, forms the ions. So I'm going to write it as like another equation connecting with this main one. 2 plus gas and then 2 Br minus gas. And then lattice enthalpy change when 1 mole of ionic lattice is formed. So this is our product of the lattice enthalpy from its gaseous ion. So here's the cycle. Then what can we do? We can either consider a linear, but we don't. Just imagine as a thing that you can always rotate because we want to find the lattice enthalpy of hydration of calcium. This is the one we don't know. So we have the enthalpy change of solution, the enthalpy change of lattice enthalpy, and this is the enthalpy of hydration. So this is the part of the cycle that we want to find out because we don't know directly. Instead, we go this way around. So can you see how I'm just twisting this ABC cycle that I normally do, considering this is our main equation that we want to find the enthalpy, and these are the common one. So I hope you can see this like triangle that I'm just rotating, because this gives me already kind of an equation that requires a bit less rearrangement. And this equation is enthalpy change of hydration is enthalpy change of lattice enthalpy plus the enthalpy change of solution. Now we can extend it. Great. We have the enthalpy change of hydration of calcium ion and bromine ion. But what do you notice? A very common mistake is the stoichiometric number. You have 2 bromide ions, so you need to hydrate it or dissolve it twice. That's why this has to be times by 2. And this is a very common mistake. And then we have the enthalpy change of lattice enthalpy, and then the enthalpy of solution, which are values that we're given. Then, of course, the rearrangement. We need to find the enthalpy change of hydration. So we simply take this. Remember, it's double the value that we're given. And of course, we change the sign. Yeah, because we have 2 bromide. And this is our final equation. Of course, substituting this value to get us the right answer. If you want to give it a go, go for it. But the correct value is minus 1,579 kilojoules per mole. So common mistake, wrong rearrangement, or wrong setup of the cycle, and forgetting to times by the stoichiometric coefficient. Okay. But one thing, this is relatively simple to remember, isn't it? Hydration is lattice enthalpy plus the solution. Can you think about it logically how this makes sense considering the definitions? Because hydration, you have the aqueous ions. What are these made of? The aqueous ions. And this links back to the first equation that I wrote here. Do you remember that instead of this, I wrote it as sodium chloride as aqueous? So this gives us an idea of what is linked between the solution and the lattice enthalpy and the hydration, if that makes sense. I mean, I can visualize it. I don't know if you can too. But basically, imagine the lattice enthalpy represents the solid, your solid ionic that you put in water, and that is the solution. So lattice enthalpy and solution become one thing. And that is equal to the lattice enthalpy of hydration, so the aqueous ion. So I would suggest you to look at this equation a little bit and see how you can really combine them in a way that for you makes sense, okay? But alternatively, you can write the cycle, making sure it's right, to work out the equation, and then keep in mind to times it, depending on the stoichiometric coefficient that we have, okay? One recurring topic that occurs here is understanding the value and the sign of the enthalpies in general. And for specifically this one is the enthalpy of hydration that we can think about. Say we have two ions, sodium and calcium, okay? I would like you to think about, or better, let me give you the values of this. Let's say this one is minus 406 all kilojoules per mole, and the calcium one is minus 1579 kilojoules per mole. Okay, can you try to explain the difference between this enthalpy of hydration of these ions? Think about what would make it different. Why is there a different energy involved? So for this answer, there is only one little thing that I would say we can improve, because it's always about the nuclear charge, the nuclear attraction, which is combination of this factor. And one thing is ionic radius, because we're talking about ions. And then, higher nuclear charge, absolutely. So smaller ionic radius and smaller higher nuclear charge. So there is more attraction between the electrons and the nucleus, but then think about what is the relevant attraction, because this attraction between the electrons and the nucleus, but would be between something else, which is the water. So between the nucleus and the water, because that's the attraction that has this energy that you're describing right now. Yeah, and then so it requires more energy to dissolve in water. Yeah, but why? Because simply there is more attraction. So this is not necessary, because you've already mentioned about there is more attraction between the nucleus and water. Okay, so key points. Normally this in the exam would be like a couple of marks. Mention the ionic radius and the nuclear attraction or nuclear charge, better. And then the attraction, so more or less attraction, because attraction then means energy. You could also say more energy is required to break or make something, okay, depending on the definition and what you're comparing, but that's good.